In our last class, we have got a general introduction on the simulation, and we have seen that there are different types of simulation: the discrete event simulation, the Monte-Carlo simulation, continuous simulation, all of these. Out of these, our main topic will be discrete event simulation. We spend maximum time on that particular simulation. So, we have already introduced how to the broad ideas of discrete event simulation, where events do occur. So, we will continue that discussion, and towards the end we shall see some examples of Monte Carlo simulation, and thereafter on subsequent lectures we will continue the discrete event simulation discussions. So, if you really let me in fact go back to our previous discussions, that in our previous class we were towards the end, we were discussing the steps of discrete event simulation. What we found, that in the beginning we have problem formulation, after that model building including of conceptualization, data collection, translation, verification and validation. Then comes the experimental design, model runs, etc., and finally implementation. Now, apart from this conceptualization and things like that, when it comes to actual experimentation, then there are basically two broad synchronization method which must be understood. One is called the fixed time incrementing method, or so called FTIM. The other is called a variable time incrementing method, or VTIM. Let me try explain exactly what we mean by them, right. So, let us say that we have a particular queuing system simulation. What we are trying to do is we are doing a queuing system simulation. Right. So, in a queuing system simulation, so you see this is the time dimension, this is t equal to 0. Now, what really happens? You see, what are some events? There are 3 events. First event is customer arrival. As the customer arrives, customer can do two things. The customer can actually join a queue, or the customer can actually join the service directly. Is it all right? These are the two things, that the events that can happen. Now, the second event that happens, the customer joins service, that could be a second event. And the third event, customer leaves service, right. Now, obviously, there is a set of random numbers. What are random numbers? How we do random number experimentation? How we generate arrival? How we generate service, etc. We shall discuss later. But let us say what we have found out, the customers are arriving, let us say like this, arriving customers, right. So, let us say inter arrival times. Suppose the inter arrival times generated are 2, 5, 7, 12, 15, right. And we also generate what is known as service times. So, what could be some service times? The service times could be arbitrarily, say 3, then 5, 4, 2, 6, right. So, if these are our obviously inter-arrival times that we have chosen, maybe too many, last one is really very high. So, let us make it only 5 and not 15. So, 2, 5, 7, 12 and 5, and service time 3, 5, 4, 2 and 6. So, really what exactly it means, that you see the first customer arrives at t equal to 2. So, this is 2. So, you see first customer arrives. So, after first customer arrives, what does the customer does? It directly joins the service, right, and it takes 3 minutes. So, what will happen? The first customer to be serviced will be at t equal to 5, is it not? So, you see during this time there is one customer who is in service, is it not? One customer is in service during this period. But when the second customer is arriving, let us say second customer is arriving after 5 more minutes. So, it is 5. So, this is where the second customer arrives at t equal to 7. How much time is required for service? 5 minutes, right. So, this particular customer will leave at here, that is t equal to 12. Look, so this is the 5 minutes. So, this is where the second customer get serviced. That is about, at this point of time there is one customer. So, again the next customer is arriving after 7 more minutes. So, if 7 it has come, the next customer is coming at 14. So, you can understand, and this customer is again taking 4 minutes of service, because during this time there is nobody in the system. So, here the next one will become 14. So, here this 18, t equal to 18, this is the 4 minutes. So, like this the system will go on, and what is really happening, we are able to generate the arrival, a customer is coming and second customer is coming, third customer is coming, first customer is getting serviced after certain 5 minutes, the second 3 minutes, second customer is getting service after 5 minutes, next customer is getting service after 4 minutes. So, all of these things are happening. Actually, all these things can be done by inter-arrival time generation 2, 5, 7, 12, 5 and service time. After that, we can do the detailed processing about queuing and things of that sort. But what is interesting to note here is that how do we track the system? One method could be, we track at every minute we track, that is, you see this is t equal to 0, we see nothing happens, then t equal to 1, nothing happens, t equal to 2, suddenly what we find, one customer has arrived. So, note that yes, one customer has arrived, t equal to 3, nothing happens, 4, nothing, t equal to 5, suddenly I find yes, that customer goes out of service, right. So, this is t equal to 5. Then again you see t equal to 6, nothing happens, t equal to 7, another customer has now arrived. So, look, so like this, if you keep tracking the system, that is called our fixed time increment method. So, probably you can now look at the slide. What is fixed time increment method? Begin the system in initial state, please look at the slide, that is begin system in initial state at fixed point of time, advance system clock by a small fixed amount of time, and update system from events occurred in elapsed time, and determine resulting system state and repeat the last two steps as many times as desired. So, this is called the fixed time increment method, right. So, what is happening? The system clock is advanced by a fixed amount of time every time and look whether anything has happened during that 1 minute time, is it not? Some event can occur, either a customer can arrive or customer can join queue. In the example, we found nobody joins queue as such because arrival times are too distant, is it all right? But service times on the other hand, they are not so high, rather low. So, queues were not formed during that time. So, only two events were generated, one is customer arrives and customer goes out of service, is it all right? Anyhow, so if we see every minute and account the system, that is called fixed time increment method. Let us look at the other method, which is called the variable time increment method. What happens here? What happens here is, look at this, the diagram that we have drawn. You see at t equal to 0, system starts. Up to t equal to 2, nothing happens. So, we have already generated mental this plot, in our mind or maybe somewhere, and we actually know that things are happening at t equal to 0, at t equal to 2, at t equal to 5, at t equal to 7, at t equal to 12 and t equal to 14 and t equal to 18, right. So, things are happening only on these times, right. T equal to 0, system starts. T equal to 2, first customer arrives, right. T equal to 5, first customer goes out. T equal to 7, second customer arrives. T equal to 12, second customer goes out. T equal to 14, third customer arrives. T equal to 18, third customer goes out. So, this is what is happening in variable time increment method. We are really changing the system time based on when the events occur. How do you know when events are occurring? Basically, through random numbers, we have already generated these inter-arrival times and service times, and we have created this map already, and therefore, we know, and therefore, we increment the system only at these specified times. So, now look at the slide. You can see that the next event or variable time increment method begins system in initial state at a fixed point of time, advance system clock by variable amount of time till next event occurs, update system from events occurred in elapsed time and determine resulting system state, and repeat the last two steps as many times as desired. All right. So, random numbers are needed to predict upcoming events, which are then ordered in time. Next, jump from one event to another while recording system changes every time an event is reached. So, you see, you are now getting a broad idea of how discrete event simulation is carried out, right. First, make a conceptual model, generate random numbers, generate events, and then follow either fixed time increment method or variable time increment method to really update the records, right. And finally, from there make meaningful what you call conclusions for implementation. We will give queuing examples on discrete event simulation in subsequent classes. So, basically there are three broad model levels. One is called a conceptual model, which is like in a mentally you generate that this kind of events are occurring, this is happening, this is flowing, these are the entities, these are their attributes, these are the state variables, and put them into a conceptual map. So, that is a conceptual model. Then next one you actually specify, and while specifying it has to be expressed in terms of inputs, outputs, simulation schemes, pseudo codes and equations. So, all of those. So, if you are talking about queuing, the kind of queuing parameters have to be established, what is coming, you are now becoming more exact and generating and all the relevant requirements which are required to make a computational model, right. that is what is specification model. And when all of these things are put in a final form, a computer program, that is called a computational model. So, these are the three model levels. You see, and before we proceed, we must verify the model and also validate the model. What is verifying? Verifying means, are we following all the procedures appropriately and properly? That is the model built right? Means, is the model building process is done with all the right procedures? If that is so, then that is called verification. In simple words, the computational model should be consistent with the specification model, right? Means, whatever specification is given, is the computational model consistent with it? If it is so, then we say the model is verified. And finally, the validation is the right model being built. So, computational model should be consistent with the real system, right? So, sometimes what happens, we have built the model, it is all the specifications is served, but finally, the real question it does not address. Because in the queuing model we are talking about, our real question was that is the service adequate or we have to augment the service. Suppose we do not get answer to that question, right? We generate lot of data, we simulate, we have done everything maybe correctly, but we are unable to really find out whether the service is adequate or inadequate. Then the purpose is not served, the objective is not fulfilled. So, although the model is verified, it follows the specifications, but it is not validated. So, validation also requires talk to the decision makers, really see the decision makers who are finally making their decisions about this particular system, are they happy with the model? Are they really seeing the system output and the simulation output, they are matching and trust could be built into the model, right. So, that is about verification and validation. So, not only just build a model, verify the model and then validate the model before you actually start experimenting with it. Now, with that we start with the we take a little departure from the discrete event simulation model, and now let us look a class of model which is known as the Monte-Carlo simulation model, right. We will not discuss much about Monte-Carlo simulation model. Our main discussion will be on what is known as discrete event simulation model only, but since Monte-Carlo simulation is one of the very important class of models and lot of interesting questions can be answered, let us also look at it in today's class. So, what is really happening in Monte-Carlo simulation? In Monte-Carlo simulation, we are, let us take an example. Suppose we need to find out value of pi. How do you estimate value of pi, right? Everyone has told you that value of pi is something like 3.14159 approximately. So, this value you know, but suppose you are told that estimate this value. You see, a very interesting method can be constructed, where supposing this is x direction and this is y direction, and we have what is known as an unit square. So, this is 0, this is 1 and this is 1, this is a unit square. Now, within the unit square you take a quarter circle, right, take a quarter circle and then hatch this quarter circle area, right. So, let us call the entire area as A. So, what is A? This is A, the entire area, that is the square area of the square. and area of quarter circle. Let us say C. So, what is C? This hatchet portion is C. So, what mathematics tells? What is the area of A? Area of A equal to 1 into 1 equal to 1, because this side is 1, this side is 1. So, 1 into 1, 1. So, area A is equal to 1. What is the area of C? It is pi r square by 4. But what is R? You see, what is the radius? So, this is radius, r equal to 1, r equal to 1. So, C equal to pi by 4, C equal to pi by 4. So, what is the C by A? C by A will be pi by 4 by 1 equal to pi by 4. So, C by A, the area C divided by area A is nothing but pi by 4, or pi is to 4, pi is to 4. So, this is the conceptual part is done. Now, what we do? We know what are some, we will discuss that later, that a random number is a number between 0 to 1, and we take two random numbers arbitrarily. We generate two random numbers, and let us say these random numbers are R1 equal to 0.3 arbitrarily and R2 equal to 0.7, right. So, what will happen? Suppose we find out the R1 square plus R2 square and then root over. What will be that value? You see, this value will now become 0.3 whole square plus 0.7 whole square. How much is that? Equal to 0.09, 0.09, 0.49. So, 0.58. Now, root over 0.58. Now, you see, root over 0.58, is it greater than 1 or less than 1? Very simple, it is less than 1. So, it is, if it is less than 1, then you see where will it fall? So, you see, if we plot that number, so this is 1, this is somewhere it will be 0.3, somewhere here it will be 0.7. So, you see this point will fall somewhere here. So, this is the point that we have generated by R1 0.3 and R2 0.7, and this point is within C, right. So, if you generate two random numbers, so you see two random numbers are generated, and that random number is represented by this point P1, and we see that this particular point P1 is within the quarter circle C. So, that is one point. So, supposing we are telling how many are obtained in C, how many are obtained in C. So, in this tally we put a 1 under C. Suppose the next point is P2, again we generate. So, this is another point, again it has fallen within C. So, another, like this we keep counting, right. So, 4, 5, 6, 7, 8, 9. So, keep doing experiment. So, you see 10, again maybe A also are going up, right. How many points are within A? You see there will be some points which will be within C, some points which will be not within C. So, but then within A. So, if we keep counting, obviously we know that this point is, all these points will be within A. So, whatever points we have generated, they are all within A, but not all will be under C, right. So, finally, suppose under C we have generated 75 points, 75 points, and within A we have generated 100 points. So, you see, since C by A is pi by 4, so here we get pi by 4 equal to 75 by 100. So, where an estimate of pi will be 300. So, it will be 3.0. So, an estimate of pi equal to 3.0 could actually be obtained. All right. Now, question is that it is only 3, it is not 3.14. Then what really happens to our calculations? Let us look at it once more in this particular slide. So, what has happened? Take two random numbers uniformly distributed. Let the two numbers represent x and y coordinates. Check if point x y is inside the quarter circle. Point x y will always be inside unit square, right. So, if this is greater than 1, then it will be outside, otherwise it will be inside. So, that experiment if you keep doing, and if we simulate for 10,000 iterations, say p number of times the point falls inside the quarter circle, then estimated area of quarter circle will be p by 10,000 star 1 equal to p by 10,000. Is it all right? So, estimation of value of pi, area of quarter circle with unit radius pi square, so pi by 4. So, pi by 4 equal to p by 10,000, or estimate of pi will be 4 p by 10,000. So, that is how a simple Monte Carlo simulation can be done and a value of pi can be estimated. So, important question out here is how do you know that value that we are getting is accurate, right. You see, to get accuracy, two things are to be done. Number one is estimate number of observations, right. Estimate based on, first of all, large number of observations. What is large? Is 1000 large or 10,000 large? Probably no. For such kind of systems, maybe experiment for very large number of times, maybe even 1 lakh time, right. So, maybe iterate 1 lakh time, right. So, iterate. So, if you iterate for say 1 lakh time, then probably you estimate, let us say, value of pi equal to 3.14. But then that is only replication 1, that is only first time. Now, do it again with another set of random numbers. So, you can call it replication 2. Suppose at that time you get pi equal to 3.15. Do it again, replication 3. Maybe at this time you get a pi equal to 3.12. Do it again, maybe you will get 3.16. So, like this, do it for a number of replications by at each replication a different set of random numbers. A different set of random numbers are to be used, and while using a different set of random numbers, we can actually predict the value of pi. Suppose we might get the value of pi comes out to be 3.14, say 15, suppose it has come like this, plus minus 0.0002. Maybe for a large number of experiment, we might get an estimate which will be a mean value and a variation, right, based on standard deviations. So, these are the things that we actually get for what is known as Monte Carlo simulation. Another example of Monte Carlo simulation, let us look. So, this is called a problem of prisoner's dilemma. You see, two prisoners A and B are charged with a joint crime, and are held incommunicado. If A confesses and B does not, A is given a reduced sentence of 2 years for cooperating with the authorities, and B gets a 10-year prison term. If neither confesses, and vice versa, if both confesses, each gets 6 years. If neither confesses, each will receive only 1 year sentence. Neither can know or even control the behavior of the other. Design a simulation scheme in order to obtain expected penalties of A and B under various or varying probabilities of prisoners taking different actions, right. So, this could be another problem where you can probably use Monte Carlo simulation and try to get answers out of it, right. So, please work these out, and we shall discuss not in the next class, but later on while we discuss queuing problems, right. So, thank you very much.